This is the second example where we're looking at buffers. In this problem, I've got a buffer solution composed of the weak acid, acetic acid, and its conjugate base, or salt containing its conjugate base, sodium acetate. So I have the acetate ion, which is the conjugate base of the acetic acid. And we want to determine the initial pH of this buffer, and we're given the Ka for acetic acid. So remember, whenever we're dealing with buffers, the chemical equation that we're considering is the dissociation of the weak acid. So I've got acetic acid plus water to form hydronium ions and the conjugate base. All right, and to determine the pH of a buffer, we can use the Henderson-Hasselbalch equation. So that is that the pH is equal to the pKa plus the log of the concentration of the conjugate base over the concentration of the conjugate acid. So the first thing I need to do is get the pKa. So the pKa is the negative log of the Ka, or for this problem, is the negative log of 1.76 times 10 to the minus 5. So that gives us a pKa of 4.75. All right, so now I can go ahead and plug everything into the Henderson-Hasselbalch equation. So the pH is the pKa 4.75 plus the log of the concentration of the base, which they told us was 0.25, over the concentration of the acid, which was the same. And so what I have is 4.75 plus the log of 1. And of course the log of 1 is 0. So when the concentration of the weak acid and its conjugate base are the same, then the pH is just equal to the pKa. All right, so in the next problems, we're going to look and see what happens to this buffer when I add strong acid or strong base to it. All right, so I've got the same buffer, but now I want to know what happens to the pH if I add some number of moles of a strong acid. Now, HCl is a strong acid, so remember that strong acids completely dissociate when we dissolve them in water. So I don't really have HCl in solution when I have a strong acid, because it will completely dissociate into hydronium ions and chloride ions. And of course, I'm not really concerned about the chloride. What I'm interested in is the H3O+. And so however many moles of HCl I've added, what I'm really adding is that many moles of H3O+. So when I add strong acid or strong base to a buffer, we typically work these as two-step problems. So first, I have a stoichiometry problem where I'm looking at the reaction of the strong acid that I've added with the buffer. And when I add a strong acid, what it's going to react with is not the weak acid, it's going to react with the conjugate base. So in this problem, I'm going to have a stoichiometry problem where the strong acid reacts with the weak base of the buffer. And so the reaction that I'm interested in is H3O+ will react with the base, and that weak base is going to neutralize the strong acid that we've added. So this reaction goes to completion, and I form water plus the conjugate acid, right? So what's going on when I add strong acid to a buffer is that it's neutralized by the weak base that makes up the buffer. And so that just forms water and the weak acid. So what we've essentially done is reacted away the strong acid that we've added, and it just converts some of the weak base into the weak acid. And so this first step, I said, is a stoichiometry problem. And whenever we're doing stoichiometry, we need the moles. All right, so I'm going to set up a table to figure out how the moles of everything changes. Now, this is not an ICE table. And so I call it a before, change, and after table, or a BCA table. And so I'm dealing with the moles. And it's not equilibrium. This reaction goes to completion. So I know how many moles of H3O plus I have. But now I need to know how many moles of acetate and acetic acid I have. And so I can do that using molarity is moles over volume. And we were given the volume of the solution. We were given the concentration of our buffer components. So I should then be able to use that the moles is equal to the molarity times the volume for both the acetic acid and the acetate. So for the acetate, the moles are equal to the concentration times the volume. Remember, the volume needs to be in liters, so I converted my 250 milliliters into liters. And then that gives me 0.0625 moles of acetate. And because the acetic acid has the same concentration and the same volume, I'll go ahead and work it out, but we're going to get the same number of moles. So I can put those into my table. Of course, I don't care about the water. All right, and so this being a stoichiometry problem, it's basically a limiting reagent problem, right? The reaction is going to go to completion, and so whichever one of these runs out first is going to control when the reaction stops. So the lesser number of moles is going to determine the limiting reagent, and so the change is going to be for H2O plus and for the C2H3O2, because it's a 1-to-1, is going to be minus 0.0050. And the acetic acid is going to increase by that much. And so when this reaction is done, I'm left with no strong acid left over. I've reduced my amount of conjugate base and increased the amount of the conjugate acid. And so, right, these are the values that I'm interested in now. Right, so on the previous page, we calculated the initial pH of the buffer. And so now I need to calculate the pH of the buffer with these new concentrations, or these new moles of acetate and acetic acid. And we'll do that on the next slide. All right, and so step 2 of this problem, we did the stoichiometry part. Now step 2 is an equilibrium problem. Right, so all of the strong acid that we added is gone, and so now I'm just left with a buffer problem again. So I'm back to the chemical equation that we use for the buffer, the dissociation of the weak acid, and I can calculate the pH using the Henderson-Hasselbalch equation. I just have to use the new concentrations of base and acid that I determined on the previous slide. Now, when we do equilibrium problems, we're always working in molarity. But in this case, since the volume of the base is the same as the volume of the acid, I could convert the moles that I had on the previous slide, but there's no point because the volumes will just cancel out anyway. So when we're doing these problems, we're adding acid or base to a buffer. Since the volume of base and acid are going to be the same, I can just use the moles instead of the concentration. So it saves me a step. So my new pH is going to be the pKa that we found before, 4.75, plus the log of, in this case, we're going to use the moles because the volumes are the same. So the base we determined was 0.0575 moles divided by the acid, 0.0675. And when I do that calculation out, I get a pH of 4.68. All right, and so we can see that our buffer did a pretty good job of resisting the change in the pH. When I added the strong acid, it did drop a little bit. Remember that the pH started at 4.75, but this is a relatively small change in the pH. All right, and so the last part of the problem, we're going to look at what happens to the pH when I add some strong base to my buffer. All right, so now I'm adding sodium hydroxide. And so similar to the acid, right, I'm not really adding, when I have a solution of sodium hydroxide, I don't have NaOH because it's an ionic compound. When I dissolve that in water, it completely dissociates into sodium ions and hydroxide ions. So what I'm really adding when I add sodium hydroxide is I'm adding hydroxide ions. And so because it completely dissociates, if I started with 0.0050 moles of sodium hydroxide, I'm adding 0.0050 moles of hydroxide. Now when we added the HCl, that reacted with the weak base component of the buffer. Now when I'm adding strong base to my buffer, it's going to react with the acid. So my stoichiometry problem is going to be the hydroxide reacting with the weak acid. Again, this reaction is going to go to completion, and so it's going to form water plus the conjugate base. So again, what the buffer does is when I add strong base, it's neutralized by the weak acid in my buffer, and it forms water. Essentially, it converts some of the weak acid into its conjugate base. So I've got my BCA table again, and they told us the amount of hydroxide, and we calculated the number of moles of acetic acid and acetate previously. So I could just go ahead and put those values in that we calculated before. Right, and the water, again, we don't really care about. And remember, when we're doing stoichiometry, we have to be sure that we're using moles. All right, so in this case, hydroxide is going to be the limiting reagent because there's less of it. And so I'll be left with no hydroxide. I've reduced my amount of acetic acid somewhat, and I've increased my amount of acetate ion. All right, and so we figured out the stoichiometry part of the problem. So step 2 is the equilibrium part, and I'll use the new amounts of weak acid and the conjugate base, and we'll do that on the next slide. All right, so step 2 is going to be another equilibrium problem. I've got the same equation for the buffer. I've got the same Henderson-Hasselbalch equation. And now I'll just take the new amounts of base and acid that we calculated on the previous slide. And again, because the volumes are going to be the same, it's okay for me to use the moles here instead of the concentrations. So my new pH is going to be the pKa plus the log of 0.0675 for the base, 0.0575 for the acid, and my pH this time comes out to be 4.82. So it makes sense that I added strong base. My pH went up a little bit, but the buffer again did a pretty good job of resisting changes in the pH.